All right, good morning, everyone. So Wednesday's class, I talked a little bit about the logistics of exam 2, again, week from today. I forgot to talk about the scope of the exam, so just like midterm 1, where the scope was from basically the homework sets that we've covered, same idea here. Right? So everything up through homework 8, with really strong emphasis on everything from homeworks 5 through 8. Right? So exam 1, that was 1 through 4. This was 5 through 8. Background information like Laplace transform, Bode plots, all those things that are either we're in 3260 or early part is fair game. That's not going to be the emphasis of the exam. The emphasis is going to be what we covered since the last exam. Okay. And then when we talked about multivariable linearization, I told you that there will be a multivariable linearization problem on the second exam. No joke, there will be. Okay, that's going to be, one of the problems will have that, right? So if you go to the review sheet, I think there's 3 to 4 examples on there. We've had examples of homework. And then just a few minutes ago, I decided that to put more information too, we had last year, so this year the project had a pretty simple linearization problem compared to other ones. And so last year on project part 2, there's a fairly complex one. And so I put up the solutions, where to go? The solutions to project part 2 in the folder called midterm 2, which is basically preparation materials for midterm 2. So you can see the solution to the project part 2 from a year ago that had a pretty complex multivariable linearization problem in there to give you more practice. And then, so both the problem statement and the solution are there, if that helps, in terms of giving more resources. Any questions about the logistics of midterm 2? Okay, so basically same deal as last time. I'll send you the front and back of the test the night before or earlier. Should run pretty much the same way. All right. Okay, so on Wednesday we didn't get as far as I wanted to. So we had Instructor Lake kind of give the introduction to the root locus. I realized, or I heard that for those of you who were in the very first section, there were some technical difficulties, so you didn't get to see this awesome animation I'm going to show you in a second. But we're trying to introduce this idea of the root locus, and as an informal definition of the root locus, kind of as a start, we'll get to a more formal definition later on in the class. But this is a graphical method to examine how the poles of a closed loop transfer function evolve as a function of a single parameter. And we give this single parameter the variable name k. Okay, so kind of put this in context of things we've gone through before. We've talked a lot about proportional control. We haven't talked about the derivative, integral term, all that much yet. We've talked a lot about proportional control, so that would be a single parameter which we could tune. And so you saw as we modified the value of Kp that the closed loop poles moved around in the complex plane. Right? And so we kind of had some observations about whether or not they become more oscillatory, less oscillatory, etc. And now this is going to be a graphical method to understand that relationship with a little bit, I guess, better specificity, right? So we're going to actually understand exactly where they're going to go as we move this parameter k. And so then Instructor Lake gave this example. This is the aerospace example. This is looking at an autopilot control system. And so this was the transfer function that was given. This is the transfer function between the pitch attitude and the elevator angle. Elevators are these little control surfaces on the back tail of an airplane. The exact system that this pertains to is not all that important. What's important for this example is to understand what the system looks like from a feedback control perspective, and that we have some sort of desired pitch attitude. So we usually call this R as a reference, but if this is an angle, maybe it makes sense to call this theta D. We have some sort of control system. This is a really simple controller. If it's just a proportional gain, okay? And then we have our plant, which is the airplane itself. Which then gives you the actual pitch attitude. We'd have some sort of sensor in here, like a gyro, to measure what the pitch attitude or some other type of tool like that. And then what we're looking at is how do the closed loop poles move around in complex plane. How do closed loop poles move in complex plane as we vary K? All right, that's the question we're trying to ask. Sorry, the question we're trying to answer. So closed loop, just to remind you what we mean by this, what I mean by closed loop here is I say this is the poles of theta over theta d, right? Okay, so our reference is some desired pitch attitude, our output some actual pitch attitude, and we don't know the relationship between them. In particular, we don't know the pole locations. Okay, and so we're going to start to build up relationships between what we call the open loop poles. The open loop poles would be the poles of some G2 and the closed loop poles. And then what Instructor Lake showed you is this kind of really simple dumb code I coded up to try and demonstrate this. And so what this does is it takes the transfer function, and I'll type this, I already have this typed in, we'll show this in a second. This is the transfer function as given in the problem statement up here. And then it looks at the root locus plot, and we'll talk about the root locus plot in a second, as we vary the value of this parameter k between these values. So the very first one, if this is our plant transfer function, which matches the statement in the problem, and if I want to look at my homemade root locus plot, what this shows is the first thing it does is it plots the open loop poles in zeros. All right, so we had complex conjugate poles near the origin, complex conjugate poles farther away from the origin, and two real poles in the system. And then what it's going to do, and this is just going to run for a little bit, is that the tip of these blue lines, and we'll call these lines the root locus, the tip of these blue lines are the closed loop pole locations for this value of k. And I'll run this for longer in a second. We'll see how this evolves. But that's the basic idea here. Okay, so I'm going to run this again with a longer or more values of k so you can see how this evolves, but I just want to show you how this starts. So as it's going to go, it's going to increment in k, and then we're going to see how the closed loop poles move around in the complex plane as we increase this value k. All right, so let's run this again, this time running up to a k value of 7. Okay, so same image. These are the open loop poles of the plant. And then as I change value k, you can see k up in the title here. We can see how the closed loop poles are moving. It's the very tip of these blue lines. That's the closed loop pole locations as we vary this value k. And so then in recitation, I understand that you went through some observations, right? And so the observations, the main observations were that this plot, and these observations are going to hold for everything. So it's not like we're just making observations, they only hold for this case. They'll hold for every root locus system we see. That the plot is always going to be symmetric about the real axis. And that has more to do with just what the solutions to polynomials are. Because you have a polynomial denominator that determines the poles of the system, right? If you have an imaginary part for one pole, you have to have the complex conjugate of it. So if you're in the positive imaginary axis, you have to have this complement in the negative real or imaginary axis. So it's always going to be symmetric about the real axis. And then the other thing you're going to see is that here we have a case where we have 4 poles in the open loop, and we had 2 zeros. So those 2 zeros are going to attract 2 of the branches of the root locus. and then the other two are going to go off to infinity in some direction. We'll talk about what direction they go off to later, but that's the basic observations that should be made from this plot right here. Okay, and we'll formalize this a little bit better, but this is just a demonstration, and this is on Carmen, you can play with this yourself too if you want to take a look at this tool. But basically, this shows you how the closed poles move around as you vary this value, vary this variable k. Any questions about this basic idea that you went through on Wednesday? Carson?
Can you make areas if you vary two parameters?
Yes.
Where do I do that?
There's not really a Locus tool for areas, but we will move around. We will learn how to distort this map. Okay, so Carson's question is, can we make this an area? And that's getting to some of the things that we'll talk about in a second. So we have the plot right now, so I will talk about it. So, all right, we have this configuration. We have a plant. We can just tune a single variable k, and that allows us to only place poles, closed poles, along these lines. So this, if my finger's right on this blue line, this is an eligible closed loop pole location for some variable k, real variable k. This, if my finger right off it, is not. So you cannot find a value of k such that the closed loop poles are here, but you can't find a value of k such that the closed loop poles are here, or one of the closed loop poles are here. So these are all eligible solutions for the closed loop poles. All right. So now, if we have multiple parameters that we can vary, then we can move this plot around. We'll look at how we can distort this plot later on. Once we get through a lot of work with how you actually, what some of the rules are here. Okay. Any other questions on that? Okay, and so MATLAB will produce this for you as well. So this matches what we just had on the screen here. The axis is a little bit different, so it doesn't look as distorted. But if you want to plot this in MATLAB, you just say R locus, and then the plant. It'll pop up in a second. Maybe to overwrite my plot. There we go. Yeah. Okay, that overwrote my plot. Okay. Do it again. Okay. So this MATLAB will produce the locus for you really quickly. And also color code this when you have lines going. Maybe tough to see the color coding in the way at the back. And then the question I get every year, so I'll just jump your question, is how do you know this branch goes here, and then this branch goes around and goes to this zero? You don't, actually. This is actually a singularity point when they come together, and it doesn't actually matter. MATLAB, for some reason, decided that they want to color code it to make it look like this one definitely goes to zero, but you don't actually know that because at the singularity point, you don't know which direction the pole goes. So one's going this way, one's going this way. Right, so the color coding at these singularities is a little bit false. Yes? So with the MATLAB command, is it assuming that you're changing the proportional gain? So we'll talk about that in a little bit more generality, but it's assumed that you're changing a gain in your system. So like just the whole proportional constant that change your integral or derivative. Yeah. You can generate a locus for that. Exactly. Yeah. So the simplest way to look at it is proportional gain. And that's often what we'll do, is we'll say we have some dynamics in our controller, and let's just look at how the gain affects the system. And so that would say that basically the proportional, integral, derivative gain are all changing by X amount, and they have their own different weights, but we're changing some parameter that changes them all by some same factor. All right, that's going to be the most common mode which we use it, but you can rearrange the equation so you can look at, all right, how does the system change as we vary the integral gain? Or if you were to redesign some part of the system, if I were to pull out a spring and change it with a different spring, how would it change with the spring, right? So it's as just a single parameter, though. Okay, so MATLAB will we'll do this for you quickly. The next part of the notes, I'm not going to go through this because this is something that we went through from lecture 2. This is a recap from lecture 2. The main point here is that in lecture 2, we talked about complex variables, and we talked about when you're working with complex variables using the polar coordinate form of complex variables, that's going to be your friend. That statement was pretty much true up until now, and now it's extremely true with Locus methods. Right? So we're going to use a lot of very graphical methods, and it's going to be much easier to solve all these problems if you work with polar coordinates for complex variables than you work with Cartesian coordinates. So much so I've never even attempted to do Cartesian coordinates. It doesn't really work all that well. Okay, so if this is something that is still kind of fuzzy to you, I recommend you go back and look at lecture 2 and some of the content that we went through there. But the main message there is that if we have some sort of complex number, we can represent it in Cartesian coordinates, that it's its real part and its imaginary part, so you give this location S, or we can parameterize this as it's a vector going from the origin with magnitude R and phase angle theta. Right? So then we would write in polar coordinates that S is equal to R e to the I theta. Okay. So that's going to be the easiest way to analyze these systems is in polar coordinates. All right, so this goes through some examples this is verbatim copied from lecture 2. Okay, so root locus analysis. Okay, so going back to how we've been drawing closed-loop systems all along in this class, we have some sort of reference signal on the left side going into our controller, G1, into our plant, G2, which goes to our output C, which feeds into our sensor, and we'll talk about sensor goes to 1 in general. So we say that oftentimes our sensors are very good, and then this feeds back along this loop. Okay, so what we're going to do when we talk about root locus analysis is we're going to actually simplify this a little bit and say, okay, G1 has dynamics to it, right? So if this is as a proportional term, as an integral term, or if it's any other controller besides a proportional controller, it's going to have dynamics to it. And we'll talk about other controllers later in this class, but it's going to have dynamics to it. And so it's going to be functions of S. And so what we can do to simplify this problem is we say, all right, the controller has dynamics, the plant has dynamics, everything that's dynamic about this equation, let's lump about the controller and plant, let's lump into a single transfer function, to simplify our analysis. All right, I'll get into what's in between in a second. And this single transfer function we're going to call G. And then we're going to have a single variable of interest that we care about varying, and we want to understand how the poles move around, and we're going to call that K. So this is just a really generic representation. All dynamics in G, single parameter that we want to vary in K. And so that means here where the transfer function would have been C over R is equal to G1 plus, all right. Not it. G1, G2 over 1 plus G1, G2. Here we'd say that C over R is equal to K, G, 1 plus KG, where G is a function of G1, G2, where we pulled out that parameter that we care about, right? So it's everything that's in G1, G2 except a single gain on our system. Right? As in which is a simplified way of looking at it. G, we will call the open loop system. Okay, so what we mean by this is that if this feedback loop never existed, right? Someone cut off your sensor, right? So you had some sort of sense signal, someone took a scissors and just cut the line, it no longer exists, right? This would be what we call the open loop response of the system. And it's going to have poles and zeros that are a function of the poles and zeros of the plant and the controller combined. So what we're going to be doing what's called open loop analysis. We're going to look at this simpler transfer function G. So open loop analysis. G, to make statements about the more complex TF C over R. Okay, so what we know is that we have some sort of transfer function G. It is in this configuration where this line is not cut anymore. So we know it's in this configuration. We know feedback control systems always follow the same pattern. We have this configuration, so we can make statements. We can understand the properties of G to then understand the properties of C over R. Is what we're going to do. That's what we call open loop analysis. So open loop analysis doesn't mean that we're looking at the open loop plant. And understanding those properties, what we're doing is we're taking the properties of the open loop plant and extrapolating or saying how can that make us help us understand the properties of this closed loop system. And so a transfer function G, we can always say is parameterized by some gain. This is not the gain we're varying, so oftentimes this class would call this K hat. So the system innately will have its own gain associated with it. Okay, so for the airplane example that we just showed, the gain was 160, right? And that was just an arbitrary example pulled from a textbook. And it's also going to be composed of a set of poles and zeros. So we can say that G is going to be a function of K hat, its set of zeros, where we in general are going to have M zeros. It's going to be also a function of a set of poles. Where we're going to have n of those. So for your notes, m is equal to number of zeros n is going to be equal to number of poles. And then the formal definition of the root locus okay, so the root locus is the set of values of S such that 1 plus k g of S is equal to 0 is satisfied as the real parameter k varies from 0 to infinity. Okay. So if we look at this transfer function All right, C over R, if we look at the denominator, all right, so this is our transfer function for C over R. All right, so the root locus, we're trying to understand the roots of 1 plus kg. So in other words, we're looking at what are the poles of C over R, right? So the poles live in the denominator of this transfer function. So we are trying to evaluate this equation. 1 plus k g of s is equal to 0, right? Or we can rewrite this equation and say, equivalently, we're looking for the values of s such that g of s is equal to negative 1 over k. Right? Just rearranging this. And so what we're really saying is what are the values of s such that g of s is equal to a negative real number, essentially. All right, so k is a real number, it's positive. So negative 1 over k is a negative real number. And so that would be, say, this location. It has a magnitude of 1 over k, so we're looking at what are the values of s such that g of s can be written as a vector that is negative real. All right. Yes, Dan. So, okay, so you were talking about, just so I'm clear, you were saying that we have parameterized g of s, right? And we have some sort of gain on the system, right? Which is not the gain we're bearing. We're saying this one's set, right? And so the question is why does that not affect this? Okay, so we'll talk about this quite a bit actually coming up. So this will definitely have an effect on. Trying to state this without using terms we haven't learned yet. This is going to have an effect on how quickly, we saw the example where the tips of those locus, right, were the closed loop pole locations. This value is going to affect how quickly that tip moves as we vary this value, okay? It's not going to actually change the shape, and we'll talk about why that is later on. Okay, so what does this tell us if we know that g of s has to be a negative real number? What does this tell us about the phase angle of g of s for this to be true? Karsten. Plus or minus 180 degrees. All right, so we're saying that g of s is this vector, right? It's equal to a negative real number, so that means for a value of s to be on the root locus, g of s, the phase angle of g of s has to equal plus or minus 180 degrees. We can also make a statement about the magnitude of g of s, and it has to be equal to 1 over k. And so these are the, basically the phase angle of g of s is plus or minus 180. The magnitude is 1 over k. These are going to be the fundamental properties that everything that we learn about the root locus is going to follow these fundamental properties. Right. Okay. So phase angle plus or minus 180, magnitude 1 over k. Oops, get off somehow. I got a little shifted here in my notes, but implication of the definition of the root locus, g of s is equal to negative 1 over k. And then this means if I were to write g of s as magnitude of g of s is equal to 1 over k. Or I can write this as its set of poles and zeros. So we have our gain out front. This is k hat, if we want to know the magnitude of g. And then this is equal to, those of you who haven't seen this symbol before, I'll explain this in a second. This is going to be the product, I equals 1 to m, s minus zi. Okay, so this symbol, if you've never seen this before, if we say that we have product I, m, ai, this is equal to a1, a2, all the way up to ai. So it's just like the summation sign, which is sigma, right? Where that's a sum, but this is for a product, in case you've never seen that. Denominator, product s minus pi, and then phase. So we know that magnitudes, this is going back to Bode plots and aspects of this in terms of how if we have a transfer function, it's composed of a set of poles and zeros. We know that the magnitudes multiply, that's why this is a product. And then we know that the sum, or sorry, the phase angle, they add together. So then the phase of g of s is equal to the sum of all the zeros, or phase angle of that value of s, minus those zero locations, minus sum of the phase angle of all the poles, has to be equal to 180 plus 360 p minus I, or p minus 1, where p is an integer. Okay. So oftentimes we talk about plus or minus 180 because we're only talking about 360 deviations. Here we'll quite often see phase angles that equal to 540 or 720 or some other 360, 540, 180, etc. So we're going to have sometimes multiple circles around the origin. That's why we're writing this way. Carson?
Should the upper limit in the denominator for the product be net?
Yes, thank you. Okay, so this may seem like a lot right now. We'll go through the implications of this in a second in terms of how this forms all the rules for locus plots. We're going to be doing a decent amount of this by hand, just like with Bode plots, because that is the, in my opinion, the most effective way to learn this and try to understand how, if we move, basically how the closed loop poles change as we vary this parameter k. And then also when we get into design, it's going to help us better understand, as we have the ability to move around our pole and zero locations in our controller, how that's going to affect our system as well. So we're going to start with some hand plotting examples for this problem first. It's going to be based off a set of rules, which we'll go through those rules one by one. All right. Any questions so far on this idea? All right, so we're going to build up these rules by some examples. All right, so the examples are going to be pretty generic. They're going to be pretty simple transfer functions. In your project, you're going to get to then apply these rules to something that has a little bit more physical relevance than what we're going to do with these basic examples to explain the concept. So starting off with this generic transfer function, we're going to say that we have some sort of g of s. This is given to you as here's your transfer function g of s. It has a pole at the origin and two complex conjugate poles at -4 minus 4i and -4 plus 4i. Right? And we want to plot the root locus for this. And so we're going to go through a set of rules. And these rules are, and this is all following, these first three rules actually follow some of the observations that we had for the airplane example, almost verbatim. And I realize that my notes are a little, crap, this is coming from an old textbook. I thought this was updated, but I was wrong. Okay, so if the denominator of g of s is order n, then at k is equal to 0, so this is where the root locus starts. Remember, the root locus is you're varying this value of k from 0 to infinity. This is basically telling us where does the root locus start. The root locus starts at each of the n branches of the root locus, so that each of the n branches of the root locus will start at the poles of g of s. Okay, so what that means, and I'll have to be jumping back and forth here a little bit to this plot that we're going to draw this on. Page 11. Okay, so what this means if we have a blank root locus plot, a blank root locus plot is just the complex plane, nothing fancier than that. And then an appropriate coordinate system for this Okay, so what this means is that when we start these root locus plots, we're going to just plot then the open loop poles and zeros. So we have an open loop pole at the origin, right here, and then we have two complex conjugate poles, -4 minus 4i, which is approximately here. This is 2.5, so it's right around here. And then we have -4 plus 4i. Right? So this is where the branch, this is where our root locus is going to start. Okay? So if k is a really small number, the closed loop poles are going to be really close to the open loop poles, is what this first rule is stating. Okay, second rule follows the example that we showed before, is that k goes to infinity. We have n branches of the root locus. These branches will either approach a 0. Okay, so this specific example does not have any zeros. So there are no zeros for these branches to be attracted to. Or they're going to grow unbounded. So that means they're going to go off to infinity. Okay, so since we have n poles and no zeros, we're going to have 3 branches of the root locus that go unbounded or off to infinity. All right, so there's nothing here for me to really plot here, except we can just say noted here that this is going to happen. Right, we're going to have 3 branches going off to infinity in this example because we have 3 poles. And then once we have this information about okay, how many of these branches go off to infinity, we can try to understand in what direction do they go off to infinity. Right, so the way in which we determine this is we can figure out in what direction or what asymptote these unbounded poles will follow, and it's given by this equation here. So if we have poles that go from, so basically we have 3 different angles in our example. Here's the more general equation for this. And this is, it's better to say, let's do I. Okay, so we're going to evaluate this equation for how many branches go off to infinity. Okay, so for this specific example, we have m is equal to 0 for this example, n is equal to 3. So by evaluating this, we're going to get theta 0 is equal to 180 plus 0 times 360 over 0 minus 3. Right, just evaluating that expression. That's 180 over negative 3, which is negative 60 degrees. All right, theta 1. (180) plus 1 times 360 over 0 minus 3. This is equal to then 540 over negative 3, which is equal to negative 180 degrees. And then theta 2. (180) plus 2 times 360, which is over 0 minus 3, which is equal to 900 over negative 3, which is equal to actually 60 degrees. Right. So just to kind of know what we have here, right? So the root locus has to be symmetric, right, about the real axis. So if we have a negative 60 degree asymptote, that means we have to have a positive 60 degree asymptote. The 180 can live by itself because that's symmetric about the real axis. Then? 900. Yeah, so the angle will be negative 300 or positive 60. Okay, so what this means in terms of applying the root locus, or I guess we're not really applying the root locus here, we are drawing some asymptotes here. I can't draw these asymptotes yet because I don't have the intersection of this asymptote, but just to kind of give a sketch of what this will look like when we do have the asymptote of these, or the intersection of these asymptotes. We're going to have one asymptote going off at positive 60, other one going off at negative 60, and then the last one going off at negative 180 degrees. And so the other thing to point out here is you may notice a pattern that you can have, that basically these angles are a function of the difference between the numbers of poles and zeros. Okay, so if your number of poles and zeros, or so the difference between numbers of poles and zeros, so is if n minus m is equal to 1, I'll just draw a bunch of these coordinate systems here. Okay, so if n minus m is equal to 1, your only asymptote is going to be at negative 180 degrees. All right, if n minus m is equal to 2, the asymptotes are going to be plus 90 and negative 90. And then our case that we just showed right here, it's going to be at plus 60, minus 60, negative 180. And then if it's equal to 4, they're going to have minus 45, plus 135, plus 45, minus 135. Okay, so you're going to see a pattern. If you go up to 5, it keeps on going, etc. But you see this pattern evolve. So you can, if you want, you can evaluate this expression every time, or you can just kind of learn these rules in terms of how the asymptotes evolve. And it's only a difference. It's only a factor of the difference in the number of poles and zeros. Yes. You can have equal number of poles and zeros, yes. Then there are no asymptotes, right? Because that's the case of every single pole has a zero that matches, so the root locus will be attracted by those zeros. improper system. Okay, so we have asymptotes. We need an intersection point. So intersection point is given by the summation of all the zero locations minus the summation of all the pole locations over the same factor, m minus n. Okay, so for this particular example, right, so we have no zeros, so the first summation term will be equal to 0, nothing there. And then we have poles at 0, and then -4 plus or minus 4i. So filling out this equation, I have a 0, because there are no zeros, minus then 0 plus -4 minus 4i plus -4 plus 4i, all over 0 minus 3, right? And so plus or -4i plus 4i cancel out. This asymptote will always be on the real axis. That's because if we have poles or zeros, they're always going to have a complex conjugate. Imaginary parts are always going to cancel out. And so what I have remaining is I have -4, but I have a negative sign out front, so that's a positive 8. So -4 and a -4 gives you -8, negative sign out front, positive 8 over -3, and so that means our asymptote is at -8/3 in this particular example. Okay, so now we have an asymptote. Now we can do something like that. So -8/3, right, is what is that, 2 2/3, right? So 2 2/3, this is 2.5. Let me use a different color for a construction line here. This is -2.5, so we're just a little bit to the left of -2.5. So this is going to be our asymptote. This is sigma A. And then I have my asymptotes going off at -180. And then I'm going to have plus 60 degrees. Minus 60 degrees. This would be okay. And so that's it. Those are our construction lines. So we haven't gotten to how the root locus then follows these lines here, but we can make an observation here. If we say that the root locus is going to follow these asymptotes, and that the root locus gives you how the closed loop poles travel as k gets large. So going back to rule 1, as k is small, the closed loop poles are going to be very close to the open loop poles, but as k gets larger, it's going to then follow these asymptotes. What does this tell us about our gain on our system? If our gain gets too large, what's going to happen to our system in terms of stability versus instability? I hear people whispering it. They want to make a loud, unstable, right? Okay. So I'm just going to draw something, I'll erase it because we need to talk about specifics on how the root locus is going to travel. But basically, one of the branches is going to follow this asymptote. And that means that the closed loop poles are going to follow this line. So as k gets sufficiently large, our system is going to go from being stable to unstable. because the closed loop poles are going to cross into the right half plane. Okay. So what that tells you, if we look back at this map I drew here, if you have any system, and this is any system that has 3 more poles than zeros, you can choose a gain large enough that the system goes unstable, right? Because it has a plus 60 and a negative 60 asymptote. That means it's going to eventually follow those trajectories, and so you can choose a gain large enough it's unstable. Same thing with 4, right? If it's 2, then it has some more nuances of whether or not there's a gain that makes this stable or not. But you could have situations where even if you increase the gain to infinity, theoretically the system never goes unstable, right? But anytime you have 3, 4, 5, etc., there is going to be a gain where the system is going to go unstable because it's going to follow that asymptote into the right half plane. Okay, so we'll erase this because we haven't drawn exactly what this looks like. Okay, rule 5. So that was rule 4. Okay, so rule 5. This is one that no one likes, but once you see this a few times, you'll get the hang of it. The wording is very strange. Okay, so on the real axis, the root, I'm missing something. The root locus is to the left of an odd number of zeros and poles. This one's not too easy to prove. The other ones have proofs associated with it. But let's talk about how this is actually manifest in terms of drawing these. Okay, so on the real axis, the root locus is to the left of an odd number of poles and zeros. So the way in which I find to be easiest to plot this is I just start from the right, and then I work myself to the left. Okay, so on the root locus, on the real axis, the root locus is to the left of an odd number of poles and zeros. If I take, say, a test point here on the real axis, and I say, all right, how many poles and zeros am I to the left of? Well, there are no poles or zeros to the right of me, so that's 0, right? I'm to the left of a 0 poles and zeros. That's an even number. So the root locus does not exist here. Right. If I then move to the left, and when I cross over the pole of the origin, I can now assess this again and say, all right, how many poles and zeros am I to the left of? Well, I'm to the left of 1 pole. That's an odd number, right? So that means, at least until this point, the root locus exists on the real axis. All right, and then I cross over and I look at, all right, as I go from negative 3.99 to negative 4.01, crossing over these 2 complex conjugate poles, I say, all right, how many poles and zeros am I to the left of? Well, now I'm to the left of 3 poles and zeros, which is again an odd number, right? So the root locus on the real axis is just going to continue on. And so in terms of this root locus plot, we have figured out what one of the branches does. We'll talk about the other 2 on Monday because I'm out of time. Okay, but this says, as I increase this gain k, the closed loop pole associated with the pole of the origin is going to move to the left, and it's going to keep on moving to the left. Yeah, all the way to negative infinity if I keep on cranking up the gain. It says nothing about the other branches yet, but it says something about this branch. All right, any questions about that before we adjourn and go off to our weekend? Okay, see you on Monday then. Have a nice weekend.